Hello and welcome back. So now really we are towards the end of our sessions, and we started these sessions by solving some simple 1D problems in finite elements. We developed our 1D code from scratch, and then we also extended it to Gmesh 1D, and then of course that allowed us to go to the 2D Gmesh, which is really a very simple port from 1D. And we also defined our shape functions. We saw how to derive them. Really the same procedure whether we are going from 1D to 2D to 3D. Really the same Kronecker delta and partition of unity property. So of course we are only looking at Lagrange shape functions here. So really the same process to develop them and even to go to higher orders. And really we just have to make the change in the shape function library and in the quadrature rules, and we can just crank up the order. And we saw how to do this, how to go from 1D to 2D to 3D, and also refining on the polynomial level. So it's really easy how to use quads or how to use triangles, how to use the Jacobian of transformation for judging the mesh quality, how to look for the angle of your elements, the skewness, the aspect ratio. So we looked at all of these different fundamentals, and we also developed a 2D code from scratch in MATLAB, which was also ported to Julia and Python. And then we also extended this to 3D, where we used it for a simple solution. So really we are equipped now to look towards a slightly more practical angle, and that will be by using FEniCS. So if you are from a finite volume background, you might have, of course, you know about OpenFOAM, which is a very famous software, right? Because it's very robust and it's a freeware. So you also have these fantastic commercial tools like Abacus or COMSOL or ANSYS. So those are of course licensed ones, and you have to pay for it. As against that, you have these free softwares like FreeFEM, which is also good. And FEniCS is also equally good, but really the idea is to use something which is more beginner friendly, and I think FEniCS is more beginner friendly. So let's just start off by developing some simple scripts which we can run in FEniCS for solving our problems. So we'll start off with a very simple problem first. And really the idea is to understand FEniCS for solving our really complex problems, which are real world problems. So the next course will be on Navier-Stokes. Even there we'll develop codes from scratch, and then we'll go to FEniCS. So this is a good approach to help us understand first the nuts and bolts of the method, and then go towards something that's more of a practical scale transfer. So here really we'll be talking about a very simple 2D problem which we have already solved. So this is just these two circles in an infinite domain, and we are just solving our Laplace problem, or you could call it as a diffusion problem. So we are just solving, if phi is our unknown, so we are just solving del square phi is equal to 0. Okay, that's the partial differential equation, and it's a steady state equation, very simple. And we have considered an infinite domain, so of course we have to truncate it, and typically we use a truncation which is 10 times bigger than our largest radius, and that's enough. And really our aim is to compute the flux on the boundaries, right? And we have already done it as part of the course by using a reaction force approach. And now we'll just do that again in FEniCS by using reaction forces, and also by integrating the flux actually on the boundary by using a boundary integral. So this is the problem, right, which we have solved, and now I have just put some numbers on it. So you have this circle with radius 1 at the origin, and at x equal to 2.5, y equal to 0, you have this other circle, and you have these two Dirichlet boundary conditions. And we have seen that this has an analytical solution by using conformal mapping, and I had also presented that analytical solution to you. And we had also seen how it starts matching the FEM solution as you start increasing the boundary, right? As you start basically using a larger and larger domain outside. And so basically you have a truncation error, and you could actually basically zero out this error by just perfectly imposing a Robin boundary condition, but that's not really easy here because we are having two poles here, right? It's like a dipole problem, so it's not easy to find out the Robin boundary condition, and also we have this a logarithmic solution, so slightly more complicated because these are like infinite line sources. So we'll just use a truncated domain here again and just define zero flux boundary. So we have also seen that this is just like your do nothing boundary condition. So let's just do this on FEniCS step by step, and our objective is to calculate the flux at this circular boundary, and we have seen that the analytical solution is basically 137. So that is the flux which is leaving this cylinder for this specific geometry, of course. So this analytical solution is 137 when you integrate the flux on this boundary for the hot cylinder, and again the same is basically received on the cold cylinder. Okay, so so let's just start developing a very simple script in FEniCS, and then we can just run this. So I am of course in the Ubuntu environment, and this will I really recommend you to use this environment, and I'll also provide this script as ready to use, but I can really say that this will run on the Ubuntu, but if you're running it through Docker or maybe on a Jupyter notebook, which is I mean through Windows, so you might face some hiccups here. So I'm using a Python interpreter, Python 3 here, so so that will make this really easy. So let's just start off. So let's begin by first defining a workflow.